Well, thank you for your introduction, and thank you to the organizers for this very nice conference. As you have said, I will talk about the Aharonov-Bohm phase shift in such an asymmetric waveguide quantum ring. And I work with Saskia Fischer and Ulrich Kunze at the Ruhr University in Bochum, and we are very happy to work with high-quality samples grown by Dirk Reuter and Andreas Wieck. To begin with, I would like to motivate this. One fundamental aspect of mesoscopic physics today is to study the interaction effects between different low-dimensional electron systems. And to study these interaction effects means to study coherence and phase changes induced by these interactions. The question that arises then is, how can we detect such a phase shift? And there are possibilities, and I pointed out two. One favored by the Heiblum group makes use of an open geometry Aharonov-Bohm ring, and another one makes use of an Aharonov-Bohm ring in a multi-terminal geometry. We will now focus on an Aharonov-Bohm ring made from a waveguide, or made from waveguides, and I will show to you that we are able to detect a phase shift in such a ring device. Our device looks like depicted in this sketch, and I just want to point out a couple of things. We're working in a one-dimensional system here, one-dimensional in the inner part of the ring itself, as well as the leads. And this is a specialty of our structure. We have quantum wire leads of the same dimension as the waveguides itself. And then we have a two-dimensional electron gas adiabatically connected to these quantum wire rings. Our structure is an etched structure, etched from a high-mobility gallium arsenide, aluminum gallium arsenide heterostructure. And we will focus on two devices, one with broader waveguides and a second one with thinner waveguides. And then I would like to point out that the complete structure is covered with one global gate to change the electron density in the device. We did two kinds of measurements. On the one hand, we did measurements in the nonlinear regime. That is, we used DC voltages and currents. That is, we used a semiconductor parameter analyzer and injected a current via a push-pull voltage. On the other hand, we used an AC signals to work in the quasi-linear regime with low excitation currents, usually in the range of 5 to 10 nanoamps. And then you can imagine three different measurement setups. And we measured in these setups. In the first one, we measure a voltage drop along the current path. This is why this setup is called the local configuration. In the non-local configuration, we measure the voltage drop down here, that is away from the current path. And then you can imagine a mixture of both, in which we will see that inertial ballistic transport competes with diffusive transport. So let's look at these DC measurements. Here you see a VI characteristic in the local setup, in the DC, that is in the nonlinear transport regime. And we find a rather regular ohmic behavior, except for this little nonlinearity around zero current. And we'll see in the non-local setup that this nonlinearity is much more pronounced. So let me remind you, in the non-local setup, we introduced the current up here, and we know that the electrons have a free mean path which is much larger than the complete length scale of the device. So electrons will not be able to follow the electric field around this corner, but rather be injected in the opposite lead, eventually end up here, and induce an enhanced voltage when measuring this VI characteristic. And we find this non-local effect, which you could call bend resistance, as long as the current is small enough. When we tune up the current, we're working with hot electrons that which enhances the scattering at phonons, so that we have a reduced slope and work in the diffusive transport regime. And this slope is the same as when we purely work in the diffusive transport regime, that is at higher temperatures. In this case at 77 Kelvin. So here we can state that we do have an inertial ballistic behavior at low currents. But actually we want to stay in the linear transport regime, that is, apply a small AC signal in this regime around zero DC current. And if we do so, we can measure the non-local transfer resistance and apply a perpendicular magnetic field. And what we do is we introduce the Lorentz force to the electrons so that this signal, the non-local signal, gets suppressed above a certain critical magnetic field. And I would just like to keep in mind that as long as the magnetic field is small enough, this effect is still valid. We can work in this non-local transport regime. And, well, to finish this, let's look at the cross-local setup. Here we find, again, in the high current regime where we have enhanced scattering, a rather regular ohmic behavior. But we find this nonlinearity, and for some gate voltages, even a negative slope around zero current. This is why, or this is the situation where the inertial ballistic transport competes with the diffusive transport component. But again, let's stay in this quasi-linear regime, apply a small AC current, and look at the quantum behavior of the system. That is, look at the quantum behavior of a one-dimensional system. And we all know that in a one-dimensional system, the conductance is quantized, usually in units of E squared or 2E squared over H, as in gallium arsenide. And we do find this when we do a two-terminal measurement of our device, where we measure the conductance as a function of the gate voltage, that is, as a function of the population or depopulation of the 1D subbands. We do find these quantization effects in the black curve, and we relate this to the population of subbands, or you could say to the resistance mismatch of the two-dimensional and the one-dimensional electron systems. What we are interested in, however, is actually the inner part of the ring, that is the one-dimensional system of the ring itself. So this is why we also recorded the four-terminal voltages, or you could say the four-terminal resistances, the transfer resistances, as a function of the gate voltage. And here you see that independent of the measurement situation, that is the probe configuration, and independent on the leads where we measure, we find the signatures of the 1D transport at the same gate voltages. That is, we find minima and maxima at the same gate voltages, so that we can state that the mode occupation of the quantum ring itself dominates the transmission probabilities in our ring. And now I would like to focus on the Aharonov-Bohm experiments, that is, apply a small perpendicular magnetic field and record again the resistance or the transfer resistance as a function of this magnetic field. And we see that the resistance oscillates with a certain frequency, and this frequency can be found by a Fourier transform, and we find that this frequency is the same in the different measurement setups, and that it is in accordance with the one expected from our geometry, of course. What we also find is that the amplitudes are the same, that the Aharonov-Bohm amplitudes are the same in the different setups, and we believe this is due to the fact that we have these orthogonal cross junctions. And we do find some other aspects, and I don't want to go into detail. I just want to mention that we can explain these findings in a very simple approach, the Landauer-Büttiker framework, for which we have to identify different transmission probabilities, and can write down the resistances as a function of these transmission probabilities. And there are some symmetries in the structure which help us to formulate this, and we can take a look at our measurements and eventually find that the transmission probability for an electron to go from one terminal or from one lead to the opposite one across the complete structure is as large as the transmission probability to scatter right into the next lead. So we state that this is, or this gives us a strong inertial ballistic behavior, which does allow for coherent transport. But let's turn to the question at the beginning again, which considers a phase shift in the system. But before we go into detail, I would like to focus on the problem called phase rigidity, which is well known to experimentalists, because phase rigidity occurs in two-terminal system and effectively two-terminal system, where you measure in a four-terminal system, but you find phase rigidity nonetheless. Well, we know that phase rigidity is a result from time reversal symmetry, which is called the Onsager reciprocity relation. And we know that in a two-terminal resistance measurement, this leads to a symmetry in the magnetic field, a symmetry of the resistance in the magnetic field. And this symmetry, as you can see in this measurement, is given for the oscillatory part of the resistance as well as the background resistance. So in such a system, the phase is stuck to 0 pi, and we will not be able to detect a phase shift. In a four-terminal measurement, however, this reciprocity relation does not lead to phase rigidity, not eventually, but it rather leads to the fact that when we measure a resistance in a certain voltage current probe configuration and interchange the voltage current and current leads and turn the magnetic field around, we will end up with the same resistance. And you can see this in these measurements. In the one combination of current and voltage leads, we measured from negative to positive magnetic fields, whereas after interchanging the current and voltage leads, we measured from positive to negative magnetic fields and ended up with almost the same resistance and exactly the same phase situation. So in general, the system is not symmetric in the magnetic field, and the phase might not be stuck to 0 pi due to the reciprocity relation. The question now is, how can we change the phase? How can we make such a phase evolution visible? And we just made use of the most simple case, which is the electrostatic Aharonov-Bohm effect. And in our system, we can change the Fermi wavelength of electrons propagating both ways, both waveguides, just by changing the gate voltage. And you can see in this interference term, there is a cosine which gives kf multiplied with a difference in length. And due to the fact that we have an asymmetric structure and a certain amount of a non-zero difference in length, we find that we can change the interference pattern by changing kf via the gate voltage. Let's look at the experiment. Here you see the Aharonov-Bohm effect measured for different gate voltages. That is the oscillatory part in this color plot as a function of the magnetic field and the gate voltage. And in an average, we can say, yes, the phase evolves linearly, and we can state that we need around 36 millivolts to change the phase by 2 pi, which is just a minor result. But we do find this linear, this continuous phase shift. I want to point out, however, that this idea is very simple because it neglects reflections and scatterings, especially at the cross junctions of our sample. So just to prove that we have a linear phase shift, we did the same with the thinner waveguide structure, and found that with a magnetic field pointing the other direction, effectively we have a linear slope again. But also we see that there are jumps of pi, and we have higher harmonics of the frequency. And the question arises, where does this result from? Does it have to do with scattering in these cross junctions? But before we go to this question, we can just state that we can induce a phase shift electrostatically in our device, and that this device does allow for a phase detection. Well, and to focus on the scattering problem again, the group of Tobias Kramer did some rather realistic theoretical approaches to our problem, and they used a time-dependent wave package approach with where they focus on the transmission probabilities in the structure and work with the Landau-Büttiker framework, and they use a very realistic confining potential and focus on what happens with the wave packages that scatter in these situations. Well, here you see their results. You see that there are regions where the phase changes continuously, but there are also pi jumps and higher frequency components. And you can see that the result resembles our results in a qualitative manner. And this is why we believe that scattering in the cross junctions is of major importance in our devices. Well, at this point, I would like to finish the presentation. I talked about this quantum ring with the specialty that we have quantum wire leads leading to the ring. And we found that the orthogonal cross junctions play a significant role, that the asymmetry helps us to detect a phase shift induced electrostatically, and that scattering at the cross junctions of the wave packets is important. And well, as a major result, we can state that this waveguide quantum ring does allow for a phase detection induced somehow environmentally. Thank you very much.
Any questions? So if this phase shift happens already on the scattering on the entrance of the interferometer, why do you see that it's electrostatic Aharonov-Bohm? Because it's just happening at the beginning of this phase shift, right? Or different?
No, the phase shift occurs. Yeah, the phase shift occurs, or the continuous phase shift occurs due to the change of Kf by changing the gate voltage. And we can change Kf in this asymmetric structure because the waves, the length the electrons propagate are different. So the continuous phase shift is due to the to changing Kf. And other features that we see, like the higher harmonics or the pi jumps, these are related to the scattering events or changes of the scattering events in the cross junctions. Thank you.
So the next